Hello everyone, this is John Buck back with another continuous time linear systems video. In this video today we're going to talk about the time-dependent Fourier transform, which is actually going to carry us back into a lot of discrete time linear systems material, since the way we calculate these in MATLAB assumes the data has been sampled, so that we are working with discrete data even if it began as continuous. And the motivation behind this approach is that we've talked about the Fourier transform a lot, but now that we've seen frequency modulated signals, we know that in most interesting signals, the frequency is not constant with time, that it's varying over time. And so we'd like to find some way to look at the frequency content of a signal that tells us something about how the frequency varies with time. If we come back to our analogy of the Fourier transform as a recipe, the Fourier transform, when we take the Fourier transform of a whole signal, is really more like the list of ingredients. When we look at the magnitude of the Fourier transform, it's telling us what frequencies are present and how much, but it isn't really telling us where they are or when they turn on or when they turn off or when they shift or how they change. And so they can actually have a number of different signals with very similar or even the same Fourier transform magnitudes that will have be very different signals. And just to make one example I'll be using in today's videos, let me play you a sound that contains two frequencies. So there's a nice simple sound with just two tones in it, but I can make a different sound that has the same frequencies with the same amount of energy in it, but sounds quite different. So the difference between those two signals isn't what frequencies are in them, but how they change over time. In the first one, the frequencies are constant for the whole time. In the second one, it hops between the two frequencies back and forth. So that's the big picture idea. So let's talk a little more about the time-dependent Fourier transform. And I'm going to show you in this short video how it conceptually what's going on. And then I'll make a second video showing an example of how we compute them in MATLAB and plot them. So for today's class, I'm going to assume that some continuous time signal has already been sampled to give us x of n, which, even though it's discrete and it would normally be a stem plot, I'm showing here just sort of as a cartoon of its form. And again, we're assuming this is sampled from some continuous time signal. So x of n is just the continuous time signal evaluated every capital T in time, where t is the sampling interval, which is 1 over the sampling frequency. So the idea behind the time-dependent Fourier transform is we're going to break the signal into blocks, computing the Fourier transform for each short block, and then looking at how those Fourier transforms change from block to block will help us understand how the frequencies present in the signal change or don't change as the signal evolves with time. Often these blocks might actually be overlapping, we'll see in many cases. And so I'm going to think about breaking it up into blocks that I'll label x sub r of n, where this is x sub r means this is the rth block indexed on n, and we're going to assume each block has its own time counter starting from 0. So each block will have capital N samples indexed from 0 to n minus 1. And so if I draw those blocks sort of by taking apart this signal up here, I'm going to sort of use different colors to indicate them. So my first block will start from r equals 0, so r goes from 0 upwards. And so this is x sub 0 of n that will go from 0 up to n minus 1. And then the next block, I'm going to show this in the case which is often common where we have the blocks half overlapping. So this is the blue region that goes from this blue line to this one. This region is x1 of n, and that would be the next block I would take and compute the Fourier transform of that. And the way we put these together is a display. Oh, let me draw one more, and maybe block 3 would be x sub 2 of n. And so this green version indicates the region that would be x2 of n, that again half overlaps with the previous block x1 of n. We take each of these blocks and run them through a Fourier transform and then stack up their spectrum to form something called a spectrogram, which is technically the time-varying plot of the magnitude of the Fourier transform, or rather maybe the magnitude of the time-varying Fourier transform, or time-dependent Fourier transform. But those terms actually get used interchangeably. People often say spectrogram for the time-dependent Fourier transform because it's the most common version we look at. So let me sort of make a cartoon of this now. So we take the first block and run it through a Fourier transform to get a discrete time spectrum x of 0 j omega. And we saw last semester that we can, if there's no aliasing, we can convert this discrete time frequency back to a continuous time frequency, right? Where we have that big omega, which is the continuous time frequency, will be discrete time frequency divided by t, by the sampling interval, or little omega times fs, will be true for the first half from 0 to pi. And so we can get the positive frequencies, which is all we need for real signals because we know the negative frequency magnitude is just symmetric. And then we're going to continue and do this for each block, one after the other. So we take the next block, shown in blue here, and pass it through and get its Fourier transform. And similarly for the third block, x2 of n, and so on down the line. We'll just work our way through the signal with these blocks, each of them giving our Fourier transform. And then let me make some room to show sort of a cartoon of how we put these into the spectrum, a spectrogram. The spectrogram will have frequency on the vertical axis and time on the x-axis, or horizontal axis, where the frequency will go from 0 up to half the sampling frequency. And what we'll do is we'll just then plot each Fourier transform from each successive block as a vertical stripe here. So the first one would be the x0 of e to the j omega. And then the next one would be x1 of e to the j omega. And so on, filling in x2, and each one will be a stripe. Though these will make an image then. We'll tend to plot them where the different color scale conventions, often the low energy frequencies will be dark colors. The warm colors like reds and orange and yellows will indicate the high frequency. Old school, these used to be grayscale, where it would go from things that were white for the low energy background to dark in the high energy background. Or rather dark, not the high energy background, but the high energy signals would show up as. And so I often like to think this is a kind of mathematical sheet music. If you've ever learned to play an instrument and read music, we've got time running from left to right and frequency running up the page from 0 to high. So as the places get colored in bright warm colors, as I lay down each of these spectrograms as a strip, or I'm sorry, each of these Fourier transforms as a strip, it will look like I'll see the progression of tones against time, where it shows which times and which frequencies have a lot of energy present. And then on this time axis, if we wanted to think about how these are spaced, we saw that these are happening every half the block size. So this first one would be 0. The next one here would start at half a block n over 2, because if I scroll back up here, right, these are half overlapping. So I've covered from here to here is n samples. This will be at n over 2. And so that if I index it basing on the start, the second block would start at n over 2 times the sampling interval in seconds. Right, so this point here would be n over 2 times t. The next one would be n times t. And so I can label the time axis in seconds, and if I rescale the omegas so that from 0 to pi maps from 0 to fs over 2, I'll get the frequencies here. And so that's conceptually what's going on here. But I'm going to stop this video here and go to the new one. And in the next video, I'm going to show an example of actually computing this in MATLAB for the signal I played you to start with, and to see how we can see two different spectrograms, one of which reveals that the two tones are consistent and steady, and the other shows how they alternate, and how that gives us more information than just looking at the Fourier transform for the kind of interesting signals that vary in time. Okay, so that's all for this video. I'll see you in the next one.